it takes time. Okay, guys, can you see my shared screen? Zoom. The students on the Zoom. Okay, I think it's okay. Sorry for the wait, and then as I mentioned, I have a meeting in the out of campus, so I tried to be with some this class time. It was quite sorry about that. So in the previous, so actually on the in the Monday's class, I posted recorded the class for the Monday class. So I believe students watched the recorded class. So actually, in the previous class, we learned about the branch instructions. So actually, this branch instruction is very important instructions. So actually, every instruction is important, But I mean, branch instruction is a little bit tricky. So because the purpose of the other instructions, what are the purpose of other instructions? Like arithmetic instructions or data transfer instruction. So what are the purpose of these instructions? So actually, for the arithmetic instructions, so arithmetic instructions read data from register files or data from immediate data, so immediate number, and they calculate the result by the definition of the instruction, and then store the result to the destination register file, right? And then how about the data transfer instructions? Data transfer instructions read the data from the memory, and then store this write data to the register file, which load instruction, and then the store instruction, the direction is opposite, so which means store instruction reads data from register file, and the read data is stored to the main memory, so that's store instruction. But write instruction is a little bit different. So actually, the purpose of this arithmetic or data transfer instruction is that the data is changes. That means that data is manipulated. So which means, so actually in the previous class, I mentioned that when the instruction is executed in the processor, then these instructions changes the state of processor, which means the data in register files or main memory. But branch instruction is a little bit different. Branch instruction just change the program counter. So actually the program counter is pointing the instruction which is being executed by a processor currently, and these branch instructions just change the program counter. So we need to understand how branch instruction works. It's a little bit tricky, So actually, I believe every student watched the recorded lecture. So actually, these branch instructions are used for supporting the conditional if statement or the iterative statement in the high-level programs, such as the for loop or while loop in the high-level C code. So actually, the branch instructions support this type of statement. So what is the property of this conditional statement? So based on some conditions like I equals Z, executed statement, like, oops, F equal G plus H or F equal G minus H. So instructions are changing, but I mentioned that in the processor, instructions are also data. So which means these instructions are stored in the memory. So which means our instructions, the compiled instructions also includes this part F equal G plus H, and then this part F equal G minus H, because we don't know the condition of this I and J before executing our code. So this instruction and this instruction is stored in the computer, that means the main memory, and then based on this condition, this instruction can be executed or this instruction can be executed. So branch instruction just have the target piece, the target program counter, which means that if this condition, the branch condition is met, that means the condition is true, then the PC is changed to the target of the branch instruction. Okay, that is the branch instruction. And then also I showed some example code from like if state that implements the if statement, and also the code that implements while loop. Okay. Okay. And then basic code, basic block. So you need to understand the definition about this basic block, because so actually before running branch instructions, we assume that the instructions, so the several instructions are executed from top to bottom sequentially, one by one. But it's not true, because if the branch instruction is included in our assembly code, then the sequence of executed instructions can be changing. So which means that based on the target of the branch instruction, and then also by the branch instruction itself, the sequences can be changing. But some part of the code, so we can focus on some part of the code. So which means that if the first line of code is executed, the instructions in this basic block will be executed until this basic block meets the branch instruction at the end of the line. So which means in the basic block, if this first instruction is executed, then the next instructions are executed one by one sequentially. So this is the definition of a basic block, but you need to remember these conditions, the definite conditions of a basic block here. Okay, so why? Because the size of the basic block is critical for the performance of our code. Okay, so actually we do not learn about the process architecture, so now I believe you don't know how the instructions are executed in the processor, but if the branch instruction is executed, performance of our program code may be degraded. It is because the clock cycles are wasted if the branch instruction is executed. Okay, but the instructions in this block can be executed one by one sequentially. So normally instruction in this base block, it can be executed without wasting clock cycles. Okay, so it's good for the performance. So if the size of this page flag is large, then the performance will be better, maybe better, maybe better. But unfortunately, in our normal code, the size of a page flag is about 4.5 instructions. So which means that in a single page flag, this page flag includes only 4 or 5 instructions. Then the page flag may have a branch instruction at the end of the line. So actually the size of the page flag is very small in a normal code. So we need to handle the actually this branch instruction in our control hardware to improve the performance. Okay. So I briefly reviewed the what we covered in the previous class. So and then in this time, I will explain about some how functions or procedures are handled in a control processor. So what is the topic of the today's class? Supporting procedures in computer hardware. So what are procedures? So you can understand a processor is a function in high level languages. So actually, I believe everyone knows about the function in C code or Python. Okay, what is the how a function looks like? So it's the main function right here. So actually, and the C code is component actually. So every C code has a main function. So it's also a function, but I explain inside how the functions are, how functions look like in the inside of our main function. So we can define some statement in the main function like equal, and then we can have a function like a full function and a blah blah blah. So this is an example of a function, and then actually this is the some skeleton of a function. So this is the function name, and then actually no sorry, can use the int C and then C equal F. So we can define the function like this: int foo, this is a function name, and then some arguments here. And then inside the function, there are some statements or instructions. So how functions are executed in a normal high-level language code. So think like this. Function is here. A function is here, and then a computer processor executes instructions before this function call, right? So these instructions are executed, and then a processor missed this function call, and what will happen? If the function is encountered, then the instructions inside of this function are executed, right? And then the function returns some result as the result of a function, right? And then the function completes each operation, then the instructions after this function call is executed. Okay, the computer hardware needs to support this operation. So, in summary, so you can summarize the how function call works in the computer hardware is the instructions with function first. The instructions before a function call is executed, and then function is called. But function receives some arguments from the parent program, parent code. So some arguments are delivered to the function. Okay, and then if we see that this function has its own instructions, which means that instructions inside of this function should be executed, which means our compiled code also includes the instructions for this function code. Okay, but these are some different group of instructions. So which means not to call a function, then the code, the program code need to jump to instructions in a function. Okay, which means we need this jump operation for supporting a function code. Okay, and then the instructions inside of this function is executed. Then the function completes its own operations. Then we need to return to the parent code. Why? So just remember that we need return. So which means after this function call, these instructions, after the function call should be executed. So which means we need to return. So how can we return to the parent code? So which means the parent code has its own program counter for some instructions in a parent function or parent code. So which means return means that we need to jump to the PC of this instruction, just take to the function code. Okay. So now to support this procedure call operation, we need jump operation, jump instructions. So which means RISC-V also supports the jump instruction. This jump instruction is different from the conditional branch instruction. So when I explained about the jump instruction, so which means that jump to the instruction in a function, which means that function has also its own instructions. So which means that instructions in a function should be pointed by PC, program counter. So jump means that the program counter is changes to the first instruction inside of this function, right? So it's the same to actually similar to the branch instruction. When the branch instruction is executed, then the PC is changed to the target of the branch, which means that the first is the instructions pointed by this target of the branch instruction is executed, which means that the program counter is changing. And then it's the same to the function code. The function is code and the program counter is changed to the PC of the first instruction inside our function. Okay? Well, what's different? So if we use the conditional branch, this conditional branch has conditions. Okay? So if the condition is true, then PC is changing to the target of the branch. If the condition is not true, so that means false, then the PC is changing to the next PC of the next instruction, which means the PC plus 4. But function is called, so this is the unconditional jump. So actually, there is no conditions for calling a function. The RISC-V supports this function called with the jump and link instruction. So also, I missed this one thing. And then another difference is that when function completes its own instruction, then we need to return to the parent code. Okay. So what does that mean? So as I explained, actually the function is completed, and we need to return to the just the next instruction of this function code. Right. The C code and the function is completed, and the next instruction is executed. So which means when the function completes its operation, then the PC, this program counter, should be changed to the very next instruction of the function code. Okay? So what does that mean? The processor needs to remember return PC. So which means that when the function is completed, then the PC is changed to this return page. And so we need to store this return PC, return program counter. Which means this program count information should be stored in some place. Right? And then now support this operation, so RISC-V supports the jump and link instruction. So it's called the JAL, so which means it's jump and link. Okay? And then this instruction has the destination register right here, and then label of the some label in the assembly code. So which means so this label means the target PC. We need to calculate the target PC based on this label. Okay. So and then this is the destination register. Okay. So how this JAL works? So this is the unconditional jump. So there is no condition for true or false. So which means that when this JAL is executed, then PC is changed to the target of the jump JAL. And then this instruction has also its own program counter number, right? Every instruction has its own program counter number. Then we need to remember the return page. So what is the return page? It's the very next instruction. So when the function is called, then and this jump AL is executed, then it jumps to the first instruction of a function, right? Inst in full. And then some instructions are executed. Then we need to return to the parent code. Then what's the very next instruction? It's PC plus 4. Understand? Okay, so we need to return to the very next instruction of this JAL. Okay, so I mentioned we need to remember this very next PC of the next instruction. So to the destination register, so this code is X1, the PC plus 4 is stored to the destination register. So that is the definition of jump and link. Okay? Understand? Okay, so Also, the computer hardware needs to support the return from a procedure or a return from a function. So also we have to support this operation. The RISC-V supports the JALR. So which means that jump and link register. So let's see how this instruction works. So when the jump completes, a function completes instructions in this function itself, then we need to return to the parent code. So how can you return to the parent code? So with the JAL, with this instruction, the return piece is stored in the X1. Okay, so this destination register, and how can you return to the parent code? PC is updated by X1. Okay, so this JALR supports this operation. So when the JALR is executed, then this instruction is the data from this source register file X1, and then this base address or base PC is added to the offset. But in this example, we store the return address to the X1. So we can just use the PC value stored in the X1. So that means offset is 0. So with the X1 plus this offset, it's actually 0, it is stored to the PC. And then jump and link register also has the destination register. So which means that this jump and link register also stores the PC plus 4 to this destination register. But when the code is returned from a function code, then we don't need to store the next PC of the next instruction, because it's just return operation. So in this example, we store the PC plus 4 to the destination register, what? X0. What does that mean? Even though PC plus 4 is stored to the X0, but this X0 value is not changing, because X0 has always zeros, so 0 value. It's not updated. So with the jump and link register, then we can support the return operation. Okay? So I think it's good to understand how function works with the example. So this is the example code. So if we see this example code, you can find, oh, this is the some example of a function, but this example just handle leap procedure. So leap. Why this procedure is called leap procedure? So think like a tree. So this is tree. The tree has a trunk. It's a very wide kind of branch. And then on this trunk, there are many branches like here. And then at the end of the branch, we can find a leaf. So leaf procedure means that it's the last function called by another function or called by a parent code. So this is the last function. Okay, so that's why. So think like this. It's a tree. The leaf is the last part of a tree. So that's why this procedure is called a leaf procedure. So I frequently use a terminology function or a procedure, but it's the same. Okay, so I can use the both terminology. So So let's see the this procedural example. So this is the return type of function, and then this is the function name. And then as you can see, this function received the 4 arguments. Okay, G, H, I, J. And then this is the result of a function, and then this variable f is declared inside of a function. And then this statement is executed, and then f is returned. So what are required in this function? So the statement or the code inside of a function will be also compiled. So which means that the assembly code will be generated for this function. So which means it is generated, then instruction 1 in function, instruction 2 in function 3, 4 will be generated, and then the last instruction will be G, A, L, R. So it becomes the parent function or parent code. Okay, this is how the function code looks like. But if you see that this function received 4 arguments. Okay, so that is the actually input data to a function. How can we deliver these arguments? So we learned about some instructions like add, load, and some other instructions. But as you can see, these instructions just handle the registers or memory. So which means that these arguments of a function can be stored in the register files or memory also. But in this example, that we have shown that the arguments of a function are stored in the register file. What does that mean? So think like this: when the function is called by a parent function, a parent code, it will look like this. If example, and then some variable like A, B, C, D. So which means these variables are computed by a parent code, like A equal blah blah blah, B equal blah blah blah, C equal blah blah, like this. Which means that instructions before this function call are executed, and then the result, some data for these arguments are already stored in the register file. Understand? So this function is just the A, B, C, D, which means that A, B, C, D. So A is stored in the some register number X10, X11 stores the register X11 stores the variable B, and something like this. And then this function is called. Now instructions will be in this function will be executed. But the data in these registers are just maintained. So which means instructions in this function can use data in these registers. Okay, so which means, so try to understand that. So arguments. So that arguments means our data, input data for a function. So these arguments are already stored in some registers. Okay, and then these data can be used by instructions in a function. Okay, and then this is the some example operation. Oops. Sorry. So in this example, arguments G to J are already stored in the registers X10 to X13. And then, this variable, F variable F, is declared in a function. So that means that this function also needs to store some data in its own register. So F will be stored in the X20 register, the X20. So then, in order to compute the result data F, then the function also requires to execute some instructions, which means, and then if some instructions are executed, then some partial intermediate data should be stored in the registers. Okay. So X5 and X6 are used for storing some temporary data, like G plus the result of G plus H or the result of I plus J. Okay. So what does that mean? The function receives X10 to X13 from parent, and then function will store new data to X20, X5, X6, okay? And then X20 will be returned to the parent. So actually, the parent codes are executing some instructions, which means that the parent code may store some data to the register file. So and then this is true because we assume that the arguments of this function are already calculated by parent function, and then those data are stored in the register files from X10 to X13. And how about the X20, X5, X6? So problem is that the data in X20, X5, X6 can be overwritten by instructions in this function. Understand? So we don't know X20 have some valid data by a parent code, or X5 may have some valid data by parent code, but we don't know. But the clear fact is that the data in X20 and then X5 and X6 will be overwritten by instructions in this function, which means that the previous data will be lost. Actually, we need to avoid this situation. Okay, the function has its own code, its own instructions, so it's different from the parent code. But the data generated by parent code can be lost if the function is executed. And then that's the problem. So we need to avoid this situation. And then possible solution is that need to save this data. Data in these registers are stored in stack. So actually the stack is the temporary memory space. Okay. The memory space in this stack is used for storing data temporarily. Okay. So possible solution is that the previous result, so the existing result in X5, X6, X20 is stored in stack temporarily. So stack is the main memory. Okay. So main memory here. And then X5, X6, and X20 are overwritten by instructions of this function. And then x20 is delivered to the parent code, but and the function is complete its own operation. The temporarily stored data is recovered to these registers. That's how function works. Okay. The important thing is that you need to know, oops, we need to store these some existing data to stack. Okay. And this is the example code. So actually, this is so if you see this code, then you can find that this instruction is add I, SP, SP minus 24. What does that mean? Which means the SP is updated by current SP value minus 24. And then SP means the stack pointer. So when we mention a pointer, which means address in memory, okay? So which means stack pointer means that is actually the address of stack space. Okay, so in this code we use the XP, or in the RISC-V is actually X1. This is the file X1. So we used some different name convention for this X1. So we can use any name, like we can use the SP, which means that this is the X1. Okay, because so in the RISC-V, stack pointer is usually stored in X1. Okay, so what does that mean? So in this code, the stack pointer is changed. So stack pointer becomes the minus 24. So which means that we will make a room for some temporary store in a stack space, and then so stack pointer was here, but after this instruction is executed, and stack pointer is pointing SP minus 24, which means this we will have some spaces, and then the size of this space is equivalent to the address of 24, which means 24 byte, right? Understand? And then, this is the store instruction. So what is it? Why these store instructions are executed? So X5 is stored to the 16 plus SP stack pointer, and then X5, X6, X20 is stored. So what does that mean? Well, this is the stack memory, and then the SP was here, and then the SP is moved to the SP minus 24. So which means that we make a room for 24 byte. And then this is the SP plus 16. It's a destination address. So in this address memory space, SP plus 16, the X5, the data in X5 is stored in main memory, because this is the store instruction. And then X6, X20, the data in these registers are stored in the stack space. So it's the main memory. Then we can find the instructions in this function. Okay? So actually this is you can see this is very simple. So actually this code is the same to some example code we learned in the previous class. So if you see that this code, so X5 stores the X10 plus X11, but stop G plus H. So arguments are already stored in X10 and X11. So both the G plus H here, X6, and then the final result is stored in Okay, and we need to return this final result of a function. So this actually we assume that the X20 has some old data by a parent code. So the F is moved to the X10 without this data instruction. So because this is the +0, so this is the same data. So just move the data to the X10. And then so the function completes its instructions. And then what should we do? We need to restore the data stored in state space. Okay? Because this data can be generated by parent function or parent code. So we need to restore to the original data to the X5, X6, X20. Where are the original data? So original data is here and printed by stack point. So X20 is here. So we got this stack point, stack address. So X20 is recovered, X6 is recovered, X5 is recovered. And then stack pointer is also recovered to its original position because function is completed. Okay, stack pointer is also recovered. And final jump and link register instruction. So the PC+4 of the which is the return piece. The return piece is stored in the X1 sorry. Stack pointer is X2. Sorry. It should be X2 and X1. Actually, X1 is used for storing return address, return piece. Sorry about that. So X1 has the return piece value, and then this PC is taken by X1 plus 0. So it returns to the very next instruction of the function code. Okay? That's how function is executed in a RISC-V processor. And then this slide shows how data is stored in the stack memory. And then actually I already explained about this. So let's put this. And then, actually the RISC-V ISO manual defines how registers are used and are stored when the function is called, or procedure is called. So actually, I explained the registers are general purpose register, but RISC-V ISO manual will define how registers are used. So that is the proposal register. And then actually the compiler needs to follow these instructions. So that means that the proposal register defined in RISC-V ISO. Okay. Actually, the code, we have many libraries, and actually the libraries are also its own instructions, and then instructions are handle some register files. So which means sometimes we need to use other libraries, which means that we use a function defined in other libraries. So which means just the function is called in a different library. So actually these operations are also applied to the other function code. So these rules should be followed by some compilers, and then so these rules are defined in the RISC-V ISO manual. So when a function is called, then these registers actually can be used by a function instructions in a function, or instructions in a procedure. So that's all. So these registers are called temporal registers. Then is not preserved by COLE. What is COLE? So it's a caller and COLE. So caller is the someone who call a function. So they may be some parent function or parent code. And then calling instead is the function that is called by a parent code or parent function. So this is actually the passive one. Okay, so caller is the calls, who calls some other function. And the calling is called by someone, called by some other functions. So if you can see, these registers are not preserved. So which means that function can overwrite data in these registers. So actually, then if some existing data is stored in the parent code, by the parent code, then the parent function or parent code need to store these instructions in a stack. Okay, the function may not store data in these registers in a stack. And then, but these registers are called saved registers, which means that when the function is called, function needs, if these registers are used by instructions in a function, then a function needs to store data in these registers in a stack space. Okay, so these data in these registers will be stored. Okay, so I just copied this register name and then the purpose of the register and the RISC-V Python manual. And you can find the register number here. And then actually the RISC-V can support the floating point registers. And then so you can find also floating point registers, but just ignore this part because we are just handling the integer registers. Now, as I explained, the RISC-V has 32 general purpose registers from X0 to X31. But those registers have own purposes. So you can find some purposes of registers here. So region point 0 is the 0 register. So only zeros are stored in these registers. And then X1. And then as I mentioned, X1 is used for storing return address or return piece. Okay, so and then you can find also ABI name. So we can use the X0 like X and the number of registers. Also, we can use the ABI name for registers, RISC-V assembly code. So as you can see, add ISP and SP minus 10 4. So SP is the ABI name. What's SP? SP is the stack pointer. So actually this is the X2. Also you can find some other purposes of the registers. And here you can find the temporal registers and the same registers like here. Okay. Also, you can find the saver. Then what does that mean? So saver means that if these registers are used, then a parent code or functions need to store these registers in stack space. Okay, that is some responsibility of the parent code or function. So let's see this temporal register. What is the saver? Saver is caller. So what does that mean? If the data in these registers should be stored, should be maintained, then caller, that is the parent function, need to store this data to stack space. How about this for me? So if XA is used by instructions in a function and a function of a procedure, so callee need to store this existing data to the stack space. Okay, and so you can also see the save here. Okay, so actually in this example, we just take the example of the RISC procedure, but also we can also have the non-RISC procedure. So what is the non-RISC procedure? So RISC is the last part of the tree, but what is the non-RISC? So that means that a function is not a last part of a tree. So it means the function can call other functions. So that is the definition of non-RISC procedure. So procedures that call other procedures. A function can call other functions. So how can we implement these non-RISC procedures? So this is the example code of the non-RISC procedures. So it's a function name, and as you can see, this function implements the factorial and factorial. And then how can we implement this factorial function with the recursive function? The recursive function means that this function can call its own function, like here. Okay. So what is the difference? This function receives the argument n from the argument n, but this function also called its own function back, but with the argument n minus 1. Okay, so this function is called the recursive function because the function call its own function, and then also its own function call its own function is called again and again by its own function. Okay, so this is the recursive function, and then we assume that the argument is n, the argument of a function is stored in x10, and result is also stored in the x10. So, what is the issue of the non-RISC procedure? What is the issue? So, when a function is called, like true is called, then the return piece is stored in the x1. And what is the issue of non-RISC procedure? This function call also other functions. Actually, in this example, this function call its own function, like that. And this function is called by parent function. The return address is stored in the x1. And then, that function can also call that function, which means, the return address should be stored in the x1 again, because x1 stores the return address. And what's the problem? So all the data can be overwritten by new return address. So we need to avoid this situation because if we lose the return address, we cannot return. So that's a serious problem. So how can you avoid this situation? Yeah, so we can save this data to memory, so stack space actually. So stack is used for storing temporary data, as I explained. And actually this return address should be also stored. So we need to store return address to stack. So let's briefly see this non-RISC procedure example. So we can find the function here, and what is the first instruction? The stack point is adjusted, and then when this function receives the argument n, and then this function also call its own function with the argument new argument n-1. So which means that argument is already stored in x10. So original value is also temporarily stored in the stack space. Okay. So actually, in order to implement this non-linked procedure, we need to store return address x1 and then the argument x10 in the stack. Okay, that's why the stack is adjusted to the SP minus 16, and then x5 receives the n minus 1. So, and then we need to compare this argument with the 1. So we just calculate the n minus 1, and then this value is compared with the x0. So if n is bigger than or equal to 1, we need to execute here this function, this part of function. Okay. So actually we need so if you see this function, so it's defined return n multiplied by at n minus 1. So actually we need to execute this part. Okay, so here. So which means this factorial function called factorial function again with the n minus 1. It's a new argument. How can we handle this? So when if the n is bigger than 1 or equal to 1, so this case, then we jump the L1. L1 is here. Okay? And then we calculate the n minus 1. This n minus 1 is stored to the x10. Okay? Why? Because the argument is updated to the n minus 1, and then the function is called with the new argument n minus 1. Okay? So we assume that argument n is in x10. So we update the argument n minus 1 here, and then it's also stored in the x10. Then function is called again. So we use the JAL. So and then this is used for calling fact n minus 1. So because x10 is the n minus 1, it is equivalent to call a function with the argument n minus 1. And then the return address is stored. The question. Which so float counter of which instruction is stored for this x1. So you know the JAL stores the PC plus 4. Then which instruction is stored? So that means the PC of which instruction is stored. Actually, this one, with the length of time. So PC of this instruction is stored in x1. Of course, JAL is executed. And then we need to jump to the here. Then this one is repeated again and again. Okay? This is the factorial function here. And then if the n is less than 1, so this one is executed. So what does that mean? If n is 1, just return 1. What does that mean? We need to return from this function. So which means the stack point is restored, and then the 1 is returned. So because we store the return value to the x10, and then stack pointer is stored. And then return is executed. So what does that mean? What is this x1 value? Then which instruction will be executed after A is one? No, because the PC is updated with the x1. So which instruction will be executed in this case? Not next instruction. Okay, so we don't have enough time, sorry. So, now that this JAL is executed, which one is stored to the X1 address of this one, PC of this one. So, and this JALR is executed, then we need to return to this instruction. Okay. So, and the JALR is executed, and we need to return to this address. Okay. This instruction will be executed, and then the return address x1 and then x10 is restored from stack. The stack is also recovered, and then the x10 is so n is multiplied by this n minus 1. Okay, and then this part is also applied again and again. So when this instruction is executed, and what's the next instruction? Yeah, same, right? This instruction. So actually, this is really tricky. So the x1 is restored in stack, and then this x1 was stored in stack, and then x1 is restored from stack. So this process is repeated again and again. So try to understand this assembly code, because this assembly code is somewhat tricky. So usually I use this code for exam problems. So try to follow this assembly code and try to understand how the non-linear procedural code is handled by RISC-V assembly code. Okay. The best way is to just define n with some arbitrary number, and then by changing n, then you can follow this assembly code. Okay. Okay. So I will start here, and then sorry for late. Sorry to wait. And then, do you have any questions?
I just want to clarify this. Li 10x is equal to 0 to 1. Why do we need that?
What?
For the L function?
What
The L function, it has x10, x0, x1, right? It sets the value to 1. Do we need to do that when L1 already does this for us?
So can you repeat the question?
So like in the sixth one, the Li 10x, x0, x1.
Second?
Sixth.
Sixth line here?
So from the top, sixth one, yeah, that one.
Okay.
It says it to 1, but is there a need to when L1 already does it for you?
There is L1?
Yeah, the L1, 그러니까 그 L1이 벌써 n 이퀄 n-1 해주잖아요. n이 1 될 때까지. 그럼 굳이 그걸 다시 그 else equals set return value 그걸 또 굳이 해야 되나 싶어요. 왜?
이거는 일단 이제 그렇다. 그러니까 지금 요 코드가 this code just return 1. 여기서 이게 n-1이 돼 있다고 하면은 그냥 그걸 하면 될 텐데 이 코드에서는 그냥 1이 돼 있기 때문에 1을 그냥 리턴을 해주기 위해서 1이라는 그 리턴하는 그 레지스터에다가 적어주는 겁니다. 그래서 그냥 그 코드 요거에 따라서 거기 바로 그 코드의 그 모양에 따라서 컴파일이 된 거예요. 그렇게 이해를 하는 거예요. Okay, thank you for attention. See you in the next class.